Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome. You and I are about to take a scientific journey way out there, about 1 million miles away, actually, because today we are going to map out this extraordinary, invisible, protective environment we live in. It's a shield, really, that surrounds our entire solar system.
It really is something, isn't it? It's so easy to just forget that we're not just floating in empty space. We're inside this huge, dynamic, electromagnetic bubble that, well, makes life possible. It's our home. And yet so much of it is still a mystery.
Exactly. And our task today is to really unpack the science behind this layer. It's called the Heliosphere. We'll also get into NASA's newest mission to measure and map it, IMAP. That's the Interstellar Mapping and Acceleration Probe.
Right.
And what we found in the research, the materials about this mission, it's not just routine science. NASA itself apparently thinks the data coming back from this is going to, and I quote, literally rewrite textbooks.
That's the level of ambition we're talking about here. It's huge. And our source material today, it really takes us right into the heart of this very complex project. We're looking at research updates around the launch, the experts involved. We're going to dig into the fundamental physics and, the pretty groundbreaking engineering needed to try and understand our place in the cosmos.
Okay, so let's start with the basics, but let's give it the depth a mission like this really deserves. If you had to quickly define the heliosphere for someone, what is it? And what's its absolute most critical job?
Okay. So basically, the heliosphere is the sun's sphere of influence. Think of it like a giant magnetic bubble. The sun creates it by constantly blowing material outwards, and it stretches way past the orbits of Pluto, Neptune, surrounding the whole solar system.
Wow.
Its most critical role, the life-giving one, is shielding us from galactic cosmic radiation.
Okay, galactic cosmic radiation. Let's break that down. We're talking about really high-energy particles, right? Stuff traveling near the speed of light, maybe from exploding stars, supernovae, black holes, way outside our solar system.
That's absolutely right. These cosmic rays, they're incredibly damaging to life, to electronics, you name it. Without the heliosphere acting as this massive primary deflector shield, that constant bombardment would make Earth, well, uninhabitable. And it would certainly make space travel beyond, say, low Earth orbit incredibly dangerous.
So it's like our first line of defense.
It is. And actually, you get sort of a dual protection. The heliosphere deals with that incoming interstellar radiation first. It slows it down, deflects rays coming from deep space. Then, closer to home, Earth's own magnetic field provides another layer of defense against anything that gets through, or, against stuff from the sun itself. But honestly, without the heliosphere taking the brunt of that galactic threat, Earth's shield alone wouldn't be enough. It'd be overwhelmed pretty quickly.
Okay, let's unpack this bubble itself then. How is this enormous environment actually created and maintained? It's constantly pushing against interstellar space, right? You can't just inflate something that big with nothing. There must be a massive engine driving it.
The engine is the sun. And the air inflating the bubble, so to speak, is the solar wind. You need to think of the solar wind as this supersonic, nonstop stream of extremely high-energy particles, protons, ions, electrons.
All shooting out from the sun in every direction.
Exactly.
And the speeds here are incredible. We're talking often faster than 1 million miles per hour. This isn't some gentle breeze.
No, it's intensely powerful. Think of it more like a plasma hurricane, constantly blowing. And this flow of particles, which is fundamentally charged material, carries the sun's magnetic field lines out with it. That's key. So it inflates and maintains the heliosphere. The heliosphere isn't just a physical boundary. It's defined by these magnetic fields and the charged plasma inside it, all driven by the sun's outflow.
So it's an electromagnetic environment.
Fundamentally, yes.
Let's talk a bit more about the state of that environment, though. It's not smooth sailing out there, is it? It's turbulent. Our sources really highlighted that turbulence is crucial for understanding how energy moves around in space. What does that really mean here?
Right. Turbulence in space, plasma physics. It's not just random chaos. It's actually the main way energy gets distributed and eventually dissipated, turned into heat. Think of a fast river again. The main current is like the solar wind flow.
Okay.
But when that current hits something, maybe a slower patch of plasma or a kink in the magnetic field, it creates swirls and eddies. That's magnetic field turbulence.
Ah, like the river losing its main force into these smaller, chaotic motions.
Precisely. And in space, this turbulence is incredibly important. It's strongly linked to how the plasma in the solar wind heats up, and also how particles get accelerated to those crazy high energies we talked about. So we can accurately measure how fast this turbulence decays, how fast it heats things. We solve a huge piece of the puzzle in space physics.
And this brings us right to one of the key experts behind this mission, and why his specific focus is so important. Our sources point to the foundational work of William H. Matthaeus. He's the Martin A. Pomerantz Professor of Physics and Astronomy at the University of Delaware, a key co-investigator on IMAP.
Yes, his work is vital. And we should probably pause here just to note, this isn't just any expert. He was elected to the National Academy of Sciences just this year. That's one of the highest honors a scientist can get, lifetime achievement stuff.
It absolutely is. And Dr. Matthaeus' involvement is crucial and very specific. It really connects the sun itself to this bubble. His expertise is right at that intersection, heliospheric science and the dynamics of the solar wind, especially how that energy moves through the system via turbulence.
So what exactly were his main contributions to getting IMAP off the ground?
Well, his role went beyond just general theory. He was really instrumental in shaping the core scientific questions IMAP is trying to answer. He did key initial calculations, and crucially, he helped set the precise specifications for the magnetic field instrument IMAP carries.
Wow. So he's defining how they measure this invisible environment.
In large part, yes. Especially for the magnetic aspects. His focus is on capturing that really elusive data on magnetic field turbulence near Earth.
Yeah.
And also things like plasma velocities and temperatures. He's trying to quantify the exact nature of those whirlpools in space.
Got it. So if you want to understand how the solar wind actually creates and sustains this protective bubble,
You need someone who can model and measure its turbulent state accurately, and hopefully soon in 3 dimensions. And that precise measurement of turbulence, especially how it dissipates, that's the link between this basic physics and the really advanced measurement capabilities we'll get into later with the L1 constellation.
okay, this is where it gets really fascinating for me. The actual mission logistics. Where is this spacecraft going to sit to do its work? Let's talk hardware, timeline.
Right, the mission is IMAP, Interstellar Mapping and Acceleration Probe. The launch vehicle, a reliable choice. The SpaceX Falcon 9 rocket.
And according to the sources, the target launch date for this whole multi-part mission was set for September 24th around 7:30 a.m. Eastern from Kennedy Space Center. The main mission is planned to investigate these key questions over about 2 years initially, but the expectation is data collection will go on much longer.
Hopefully, yes. But the really cool part, I think, is the destination. IMAP's address is Lagrange Point 1.
Your L1. We hear about Lagrange points a lot in space missions.
Right.
Why L1 specifically? It's about 1 million miles from Earth, out towards the sun. What makes that particular spot in space so special?
L1 is basically a gravitational balancing point. It's one of 5 Lagrange points in the Earth-Sun system. Along the line connecting the sun and Earth, it's a spot where the pull from the sun and the pull from Earth, plus the centrifugal force needed to orbit with Earth, they all cancel each other out, more or less.
So it's like an incredibly efficient parking spot in space.
Yeah.
The spacecraft doesn't need to burn a lot of fuel, constantly fighting gravity from the sun or the Earth. You can just hang out there relative to us.
Exactly. That stability, that efficiency, it allows for long-term continuous measurements, which is vital if you're monitoring something as dynamic and constantly changing as the solar wind. You need that consistency to see the patterns, detect the subtle shifts.
Makes sense.
But there's also a massive immediate safety benefit to being at L1. This speaks directly to the practical side of this science.
The space weather aspect we touched on.
Yeah.
How does L1 act as an early warning system?
It's all about its position. It's 1 million miles closer to the sun, the source of the danger, than we are here on Earth. So if there's a big burst of particles from the sun, like a coronal mass ejection or CME,
Which can be really nasty for satellites and power grids.
extremely nasty, IMP and the other spacecraft stationed at L1 will see that solar storm coming before it reaches Earth.
And what kind of lead time are we talking about? How much warning does that give us?
It typically provides about half an hour's warning before those harmful particles arrive at Earth.
30 minutes. Is that actually enough time to do anything significant if a CME is barreling towards us super fast?
That's a fair question, and the answer is yes, absolutely. That 30 minutes can be the difference between major disruption and just writing it out. For satellite operators, ground control teams can use that time to power down sensitive electronics, maybe reorient the satellite to a safer angle, or even upload protective software patches. And for astronauts, especially if we think about future missions to the Moon or Mars, outside Earth's magnetic protection, 30 minutes is enough time to get to specially shielded areas within their spacecraft or habitat. Without L1 acting as that picket line, the warning time could be practically zero. The storm hits before we even know it's coming. So yeah, that L1 fleet is a critical, practical tool for protecting our technology and eventually humans in space.
That practical safety angle is definitely vital. But let's pivot back to the core science goals, the ones that NASA thinks will, as they said, literally rewrite textbooks. This mission isn't just about monitoring. It's designed for genuine discovery science.
And to back up that claim, you really have to target fundamental, unanswered questions in astrophysics, big ones. The ability to make those breakthroughs rests on IMAP's toolkit. It's carrying a suite of 10 highly sophisticated instruments. They're designed to measure pretty much everything you need to understand what's happening out there. The solar wind itself, the plasma, high-energy particles, the magnetic fields, the whole shebang.
Okay, and the research material pointed to two main, really fundamental issues IMAP is built to investigate. Let's tackle the first one. Particle acceleration.
Yes, this is a really deep mystery. Goal number 1 is understanding particle acceleration. How do charged particles coming off the sun, mostly protons and ions, gain so much extra energy after they leave the sun's surface? We know they start out fast, but something out there in interplanetary space seems to supercharge them, often pushing them close to the speed of light.
What's the current thinking on how that happens, and why isn't it enough?
Well, the standard model involves things like shock acceleration, sometimes called first-order Fermi acceleration. Imagine a particle bouncing back and forth across a shock wave, maybe from a CME plowing through slower solar wind, like a tennis ball getting hit repeatedly between two converging walls. Each bounce speeds it up.
Okay, that makes intuitive sense.
It does, but when we look closely at observations, that mechanism alone doesn't seem to fully explain the absolute highest energies we see, or how quickly particles sometimes get accelerated in specific events. There seems to be something missing, or maybe another process working alongside it.
So IM is trying to find, like, a hidden accelerator pedal in the universe.
That's a good way to put it. The instruments are designed to measure the energy spectrum, the composition, and pinpoint the location of these accelerated particles with way better sensitivity than before. By figuring out exactly where and how fast they get boosted, the hope is to uncover those missing pieces. Maybe identify entirely new acceleration mechanisms. That's definitely textbook rewriting potential right there.
Definitely. Okay, what about the second big question? Interstellar interaction.
This one is about the big picture, the boundary war, you could say. It's about how our entire protective bubble, the heliosphere, interacts with what's outside it, the interstellar medium, the stuff between the stars. Gas, dust, magnetic fields, neutral particles.
The true edge of our solar system's influence.
Exactly. The sources point out that we have a general idea of the heliosphere's shape, kind of like a comet, maybe, with a nose facing into the interstellar wind and a long tail trailing behind. But the actual physics happening at that boundary, it's still pretty poorly understood.
We're talking about the heliopause, right? Where the outward push of the solar wind finally balances out against the inward pressure from interstellar space.
Precisely that boundary. IMAP aims to provide the first really comprehensive, wide-area maps of this complex interaction zone that will help us figure out the true shape, the size, maybe even how stiff or squishy our shield is against that external pressure. Understanding that boundary is fundamental to knowing our place in the galaxy because it controls how much of that interstellar material actually gets inside our solar system.
Speaking of stuff getting in, I think we read that IMAP also has a kind of secondary measurement target. Something maybe less dramatic than a solar storm, but still important. Cosmic dust.
Yes, that's another piece of the puzzle. Cosmic dust, especially dust originating from outside the solar system, carries clues about the composition of the local interstellar neighborhood we're currently flying through. IMPAR will measure these fine particles, analyze their speed, direction, maybe even their chemistry. It's another way to sample the galactic environment, one that isn't affected by magnetic fields in the same way charged particles are.
And we absolutely have to mention the scale of this undertaking. A mission this ambitious doesn't happen in isolation.
No way. It requires a massive collaboration. The project's led by Professor David McComas at Princeton, managed by Johns Hopkins Applied Physics Lab. But the full team involves something like 82 partners, universities, research institutions, industries from all over. It really shows that pushing the frontiers of science like this takes a huge coordinated effort from the global scientific community.
That collaborative spirit and the drive for genuine discovery seems perfectly captured in something Dr. Matthaeus apparently tells his students about this kind of work.
Yeah, it's a great quote. His advice was essentially, don't just look over your shoulder, try to do something nobody else has done before. And that really sums up the whole ethos of IMAP. They're not just trying to tweak existing models, they're aiming to gather the data that forces us to create completely new ones, especially about how plasma behaves on these vast scales.
Now, the scientific payoff from IMAP gets even bigger because, as you mentioned, it's not flying solo out there at L1. This is where we need to talk about the L1 constellation. It sounds like a high-tech fleet, creating a truly revolutionary way to measure space.
It's a really clever strategy leveraging the launch opportunity. Riding along with IMAP are two other important missions. They create instant synergy. The first one is the Carruthers Geocorona Observatory. Its focus is actually looking back towards Earth, studying changes in our planet's outermost atmosphere, the exosphere.
Okay, looking inward. And the second one looks outward, right? NOAA's Space Weather Follow-On L1 spacecraft. This ties right back to that practical safety warning system we discussed.
It absolutely does. The NOAA mission is purpose-built for operational space weather forecasting. It measures those key indicators: solar wind speed and density, thermal plasma, the magnetic field, and it's specifically designed to detect those potentially hazardous coronal mass ejections heading our way.
So IAP launches with these two companions, and they immediately join the existing spacecraft already working in that L1 neighborhood.
That's the key. The documents mention spacecraft like ACE, WIND, Discover, MMS, even India's Aditya L1 mission is there now. So when IMA and its rideshares arrive, you'll have at least 6 spacecraft operating simultaneously in this crucial sun-facing location. And that is what unlocks the potential to, well, rewrite those textbooks, especially concerning plasma physics.
Okay, let's spend some real time on this because this gets into the deep physics that Dr. Matthaeus is particularly interested in. 3D plasma dynamics. You said earlier that with just 1 or 2 spacecraft, you couldn't really measure things in 3 dimensions properly. Why is having simultaneous measurements from multiple points the breakthrough?
Right. This tackles a fundamental problem in observing dynamic systems. It's often called the space-time ambiguity. Imagine you're trying to understand weather patterns, but you only have one thermometer at one fixed location.
Okay.
If that thermometer registers a sudden drop in temperature, you don't know why. Is it because a large cold front moved over your location? A change happening over time? Or did your thermometer just happen to drift into a small pre-existing pocket of cold air? A change due to moving through space. With just one point, you can't easily distinguish between changes happening everywhere over time versus changes due to moving through a structured environment. Space and time get mixed up.
Ah, I see. So without multiple viewpoints, you can't build a true 3D picture of the structure of, say, a solar wind stream or a magnetic cloud as it goes by. You can't tell if a change you measure is the whole thing evolving or just you flying through one part of it.
Precisely. And this multi-point strategy, having 6 or more spacecraft spread out over a region at L1, forming a kind of distributed sensor network, this is what Dr. Matthaeus identified as his #1 interest in the mission's potential. Once you have multiple measurement points separated in space, you can start to untangle those space and time variations. You go from that single thermometer snapshot to having a grid of sensors, allowing you to build up a dynamic 3D map of the solar wind conditions in real time.
That sounds incredibly powerful. So what is that separation, that genuine 3D insight, let them measure that was impossible before? What specific physics is Matthaeus hunting for with this constellation?
It opens the door to measuring complex, dynamic processes with much higher fidelity, especially things related to turbulence and how energy flows through the plasma. For instance, they can finally get direct measurements of the decay rate of turbulence, how quickly those energetic eddies dissipate their energy into heat. They can measure the actual heating rate of the plasma due to that turbulence. Before, these were largely things you had to infer or estimate from theoretical models. Now, with multiple points, you can measure the gradients, the flows, the structures in 3D, and calculate these rates directly from the data.
Wow. So it really is like going from a single blurry photograph to a high-definition 3D movie of what the solar wind is doing.
That's a fantastic analogy. That's exactly the goal. And that kind of detailed 3D understanding is crucial if you want to accurately predict the impact of major space weather events hitting Earth. You can map their internal structure, see how they're evolving as they approach, and forecast their effects with much greater confidence because you're not just guessing about their 3D shape and internal dynamics anymore.
Okay, let's shift focus now from looking at the stuff flowing past us to looking much further out. We need to talk about one of IMAP's really unique capabilities, capturing these special particles called energetic neutral atoms, or ENAs. This is how the mission plans to map the actual boundary of the heliosphere, right?
Yes, this is a truly remarkable technique and a cornerstone of the IM emission concept. It's quite specialized. 3 of the 10 science instruments on board IMAP are dedicated specifically to detecting and imaging these ENAs.
And why is capturing neutral atoms the key here? What's the neutral advantage when you're trying to peer into the distant heliosphere?
It all comes down to those magnetic fields again. Almost everything else IMAP measures directly, the solar wind protons, the electrons, the bulk plasma, carries an electric charge. And charged particles, as we've said, get pushed around by magnetic fields. They feel the force. They follow the field lines, spiral around them, get deflected by turbulence.
Right. So if a charged particle starts way out at the edge of the solar system and tries to travel inwards towards IMAP, the heliosphere's own magnetic field is going to mess up its path. Like trying to see through foggy glasses.
Exactly. It's worse than foggy glasses. It's like trying to trace the path of a ball bearing through a pinball machine. The charged particle's trajectory gets completely scrambled by the magnetic fields it has to cross. By the time it reaches IMAP, you can't tell exactly where it came from at the boundary. Its origin information is lost.
But neutral particles, they don't care about magnetic fields.
They completely ignore them. Because they have no net electric charge, magnetic fields exert no force on them. So ENAs are created out at the edge of the heliosphere in the region where the hot solar wind collides with the cold interstellar gas. This collision process can create fast-moving atoms that happen to be electrically neutral. And once created, these ENAs fly in a perfectly straight line from their point of origin, right through all the intervening magnetic turbulence, directly to the IMT detectors at L1. They're like messengers carrying an undistorted signal straight from that distant frontier.
Wow. So by detecting these ENAs, scientists can effectively look outward through the heliosphere's magnetic bubble without the view being distorted by the bubble itself.
That's precisely the idea. The goal is to build up an image, or rather a map, based on where these ENAs are coming from, what their energies are, maybe even what type of atom they are. By doing this over time, scientists can map the 3D structure and the physical processes happening in those incredibly distant regions, the heliopause, the region just beyond it where the solar wind meets interstellar space. Regions that are otherwise totally hidden from us if we only look at charged particles. It's really the only way to get a direct picture of the farthest reaches of the sun's influence and how our bubble interacts with the galaxy.
So IMP is doing double duty then. It's looking inward with the plasma and field instruments to understand the solar wind engine and turbulence nearby.
Right. And it's looking outward using these ENAs to map the actual shape and physics of the protective shield itself way out at the boundary. That combination, that synthesis of looking both inward and outward simultaneously with cutting-edge instruments, is why this mission is generating so much excitement. It's a truly comprehensive approach to understanding our entire heliospheric environment, from its solar engine to its galactic interface.
Okay, let's bring this all back home. Let's connect this complex science back to the practical implications for you, the listener. This huge international multi-spacecraft effort. Fundamentally, it's about understanding our environment to better protect ourselves, our technology, and our future ambitions in space.
Absolutely. We've talked about the space weather monitoring aspect. That half-hour warning from the L1 constellation, fed by data from IMA, NOAA spacecraft, and others, it's vital. Vital for managing satellite operations, protecting communication networks, safeguarding power grids on Earth. Our modern technological society is surprisingly vulnerable to hiccups from the sun.
And it becomes even more critical when we think about sending humans further out, beyond the Earth's protective magnetic field.
Definitely. This kind of research is absolutely essential for planning future human exploration. Think about the Artemis missions going back to the moon, or eventually the much longer and more challenging journeys to Mars. Once astronauts leave Earth's magnetosphere, they are much more exposed to both those steady galactic cosmic rays and sudden bursts of dangerous particles from the sun, the solar particle events.
So we need to know really accurately what that radiation environment is like further away from Earth's shield. We need to understand the risks to design spacecraft, habitats, maybe even spacesuits that can properly protect the crews. IMAP is providing the ground truth data needed for that critical engineering.
Exactly. So if we try to synthesize the big picture here, what we're seeing is this incredible leap in capability. We're moving from decades of mostly single-point measurements, that lone thermometer analogy, to having this network, this constellation of at least 6 spacecraft at L1, all working together to build a dynamic 3D understanding of space plasma.
That really seems like the core takeaway. The science team, including experts like Dr. Matthaeus, they're now facing what the sources themselves call an enormous data science problem. This mission, this constellation, it's going to generate an absolutely unprecedented flood of multi-dimensional data, far more complex than anything from previous space weather missions. It's an ocean of 3D information pouring back to Earth.
It is. And that raises a really interesting question, maybe the ultimate provocative thought for you listening. How is the challenge of processing, analyzing, and applying this torrent of new, complex, three-dimensional data going to fundamentally change things over the next decade? How will it change how we design spacecraft, how we model space weather, how we understand the basic physics of plasmas throughout the universe? The challenge of handling the big data from space is becoming almost as fascinating as the physics discoveries themselves. This is a discovery process unfolding right now that you can follow along with, happening right now at the edge of interstellar space.
It's definitely proof that there is still so much we don't know about this vast, invisible shield we live inside. And it highlights the amazing, revolutionary steps scientists are taking to finally map it out.
Indeed. Keep looking up and keep exploring that knowledge.
We'll catch you next time as we dive into our next set of sources.